Hello everyone, welcome back. Today I will be going through an example, which is a very simple example, but important to understand how to decompose the forces for a motion. And this is the example is called inclined plane, as we will see in a sec what it is. This is an inclined plane. So we have an object of mass m, and the object is onto a surface which is inclined with an angle alpha. There is a point of contact, only one point of contact here, and what we will do some approximation to start with to consider the first example. Then we can complicate it as much as we want later on. But let's consider the fact that we're not considering, well, the object will be rotating, but will be moving, but we are not considering rotations. So the object is sliding, if you want, sliding along this direction. And then we only consider static friction, meaning that the object can stay at rest for some inclination, and after certain inclination will start sliding, as I said, right, not rolling. Okay, so actually not rolling is correct. Not rolling, sliding, but not rolling. So static friction, meaning that there is no friction in the direction of the motion. So, and there is no air again. So we always forget about no air. So there is no drag. So again, with this, this assumption can be alleviated in future videos. We can introduce rotation, frictions, but it gets more complicated. The math gets more complicated, and then maybe we get to solve numerically rather than analytically. So let's keep it simple and let's see where we can get to. So let's start with the. So we said that we remove air, we only have static friction, so we have only one force. Where does the static friction comes from? It comes from the fact that the object is trying to fall down, but the inclined plane is opposing some resistance, and the resistance is in the direction of the plane, of course, and this force is, sorry, yeah, it's there, and let's put it, let's acting on the point where the other force is, otherwise the decomposition doesn't look nice. So the force is there, and this force is counterbalanced by F eta. I will tell you why it's eta, is the friction, is equal mg times, what is this? This is the, need to do some trigonometry. This is alpha. This is alpha. So this force here is the sinus, mg sinus alpha. And the friction, F eta friction, is mg eta there is a coefficient that tells us how much friction is there. So, but we don't care about this because we say that we have an angle for which this this friction is not enough to hold the mass in place. So we can say, okay, that these two forces cancel out, but the angle is bigger than some critical angle that allows for rotation. Basically, you solve this equation here, which is sinus alpha equal to eta, and then you get that alpha is related to a coefficient, and that tells you the minimum inclination for which the object will start rolling. So we are above that we have above that critical angle, so we beat the static friction, but we don't introduce any other friction. We don't introduce the friction along the direction of motion, which is this one. Okay, in this direction there is a force that is the other component of the gravitational pull, which is mg times cosinus alpha. And I hope I didn't mix up. Let's see. When alpha is 0, actually it's the other one. When alpha is 0, this is the sinus. Sorry guys. This is the sinus of alpha, and the other is the cosinus of alpha. I made a silly mistake. You can guess it from the picture, uh, or the easiest way to remember this, if you don't want to do the triangle equalities, the easiest way to remember is that when alpha is 0, the force in the direction of motion is 0, because there is no component along the direction of motion, because the ball will be resting and then will be mg. So in this direction will be 0. Therefore, that component is with the sinus, and there is maximum at friction in static friction here, because uh, the inclined plane is not helping if you want to move the object. So okay, this was a silly mistake, but we get it right. We have the cosinus, and the force that we want to use is mg sinus of alpha. Okay, so what can we do next? So let's see if we can draw some conclusion from here. So suppose we want to suppose we want F is equal m times a, and the force is mg sinus alpha is equal to m times a. So okay, so the mass simplifies as usual, because the object is moving in this direction, the mass is the same, so it cancels out. Sinus of alpha is that angle, and the acceleration. So we have that the second derivative of time over time of the space is equal to g sinus alpha. So this is very similar to the free fall, if you want, mg, because we know that derivative x square t is equal to g. And there is just a correction on the gravity, so it's like it's falling with a different speed, and this is because with a possibly smaller speed. Exactly, and in fact it will fall with the gravity when pi is equal 90 degrees, meaning that the inclined plane is like this, 90 degree, and the object will free fall, because g times sinus alpha will be equal to g. So we are all set. We need just to solve this equation easily. We get the first derivative, so the velocity of over time is gt sinus alpha plus a constant, and the constant is the initial velocity. The initial velocity is 0 in this case. We can change the condition, but let's say that is 0. So we remove the constant, and then we do another integration. So we find the x, that is the one that we want, is basically gt square over 2 sinus alpha plus initial condition. Now we can remove the initial condition easily by placing our reference frame here, x and y, and in this case x0 equal to 0, so we can remove the initial condition here. So let's see. So let's see from, so the solution is this one, that is very similar to the free falling case with a correction, which is the sine, which is the sinus of the inclined plane. As I said, if the angle is 0, there is no motion in x direction because sinus is 0, so there is no displacement. And if alpha is pi over 2, 90 degrees, will be exactly the same as a falling object. So at least in the ideal case where there are no frictions, we understand what the inclined plane is doing, is helping the motion in direction, and the maximum motion that can be achieved is the one as if it was free falling. Okay, let's do another example. Well, let's do the same example with another approach. So we know that we always know that the energy is total energy can be thought as kinetic energy plus potential energy. Okay, so there are two, and these two position time 1, time 0, and time 1 here. Okay, time 1, where the ball is after the motion, so after some time, and then we calculate in the slide before the time, because the time was well, x, it was gt square over 2 sinus alpha, so we can get the time from this equation if we know the space, for example, or vice versa. But let's suppose we want to find the solution in these two cases when the ball is up the hill, let's say, and down the hill. So the kinetic energy in the first case is 0, because energy total at time 0 will be 0 kinetic energy, because the initial velocity v0 equals 0. So the kinetic energy is mv square. This is kinetic energy. And if v is 0, the kinetic energy is 0, plus mgh. And h is this distance here from the ground. Okay, is the initial point. Mg is the mgh is the potential energy that we have. Okay, so now what is the in time 2, we have that energy total in time 2, in time 1, sorry, will be fully kinetic. It will be 1 over mv final square plus 0, because we say that this is the 0 point for the gravitational potential u, and we calculate the gravitational potential from this point here. So there is this difference in height which is h. So we have these two initial and final conditions, and we know that energy must be conserved. So E total at time 0 must be equal to E total at time 1. Okay, these two things are the same exactly because there are no frictions in place. So we are in the case where the ball is rolling, but is rolling without friction, and there is no air. So this is true. Energy is conserved because the friction doesn't remove energy from the system. Okay, so we can see that mg is equal mgh is equal to v square m divided by 2. Okay, and we can find h. We can see that, okay, so this is the velocity. So we can see that the velocity that we find at the end is equal to gh over square root of 2. But if we want to see, if you want to see where the angle went, is exactly in the definition of h, because this distance here is the displacement x. So we know that x divided by h is exactly sinus of alpha. So the h is exactly x gx divided by sinus of alpha, and this is what we can get from here if you want, with the same, what we got before is the same formula, but just the velocity. Okay, so we can retrieve the velocity from the other formula as well. So this is just to show you an example on how to solve certain problems when the energy is conserved. It's easy to, we can find the final velocity easily with this consideration here, where the energy is the same at the initial point and the final point, and this is because there is no friction. The only friction that we consider was the static friction, but we are above the critical angle, well, slightly bigger than the critical angle, for which the static friction block the motion, and above that angle there is no friction whatsoever. Okay, so with this I'm done, and I hope you enjoyed the video, and we'll see you next time for other examples. Thank you for watching.